So I'm going to be talking about microservices and Nomad and Consul. And most of the talks that I do are like how to do things at scale. So this talk is going to be about how to run microservices at scale with Nomad and Consul, and what are the challenges that microservices poses, and what are the challenges that microservices poses, especially in a large-scale data center or like a large-scale cloud environment, running in a situation where you have more than one data center, or more than you're operating on more than one region or more than one geographic region with a public cloud. So what are the challenges, and like how do we tackle them, and what are some of the patterns that I have found helpful in the past. So a little bit about me. My name is Diptanu, and I am a distributed systems engineer at HashiCorp. And currently I am working on a cluster scheduler called Nomad. Nomad is open source. And I have been I work full time on Nomad. And before HashiCorp, I used to be an engineer in the platform engineering group at Netflix, where I worked on Apache Mesos and built a cluster scheduler called Titan, which was native to Amazon Web Services. And in general, in my career, I have been mostly like a platform engineer, and I have experience as an SRE and WebOps, and experience doing WebOps at various startups. Did a lot of continuous delivery back in the day when I was at ThoughtWorks. So that's like my background. I'm very passionate about distributed systems and cloud operations, and how things have to be, and designing systems which has to be running continuously and have to be highly resilient. So this talk is going to be about microservices and architecture of internet scale applications. We are going to talk about the landscape of modern data centers, and we're going to talk about how cluster management and dynamic service discovery plays a role in that kind of an environment. We are going to do a hands-on demo of Nomad, and we are going to see how Nomad integrates with Consul. I'm not going to get into too much of a depth about Consul, because this talk is mostly about cluster schedulers and things like that. I will touch the aspects of Consul which are relevant to running microservices, relevant to running applications on a dynamic and elastic infrastructure, and why we need service discovery. But other than that, I won't delve into the internals of Consul. If you want to know more about the internals of Consul, just feel free to stop me at any point, and I can talk more about the details that you would want to know. I'll speak about Nomad internals, speak about how it's different than the other schedulers that are there currently, and things like that. So the last 10-15 years has been pretty interesting. Back in the mid-90s, I grew up in India, and we didn't have a lot of internet connectivity, but I still remember going to GeoCities and things like that to do my school homework and find information on the web. And post late 90s, the landscape of internet has changed. The internet no longer had things like directories and stuff. Instead, there were, we are so used to things like Google, and post Google, there has been services like Netflix and Twitter. And in 2009, our industry saw went through an avalanche. 2008, 2009 is when the public cloud became very relevant. And all these services, Google, Netflix, Amazon, Twitter, they have something in common. They are the term that we use to describe them are internet scale or web scale. What does that mean? It means that we no longer expect these services to have scheduled maintenance. Pretty much that. We don't expect them to go down at a particular time of the day. We don't expect Netflix to go down when we come home and switch our TV at the end of the day. We don't expect Amazon to go down because of Cyber Monday deals. We don't expect Twitter to go down when there is a revolution somewhere in Egypt. So these services like are pretty much have to be highly available. Services which are highly available, services which are highly resilient to disasters, services which are accessed by billions of people are sort of like the torchbearers of the modern applications that we sort of sought after when we are designing a new system. And they have all these things have something in common. They are built with service-oriented architecture, and that sort of like forms the foundation of their architecture. So we are going to take the example of Twitter, since Twitter has publicized the various middle tier services. So this is like a typical Twitter stack. They have like the front end load balancer, and then they have like some front end services which are basically which basically exposes the data structures that the Twitter mobile application or the Twitter website uses. And then they have a bunch of mid-tier services which has like the business logic and the more the services which power the real-time aspects of the service. And then there are services like the storage services like MySQL and Cassandra and things like that. And of course there are caches because caches make everything fast. One thing that is common across all the services is that each of the services touch many other services. So the web service, which is in the presentation block, would probably be touching the tweet service, the user service, the timeline service, and everything. There was a nice diagram that I couldn't find when I was making my slides. The Twitter architecture, when you connect all the dots, and each dots being each of the services, and if you draw lines between each of these dots, which represents the other services that a service talk to, it almost looks like a Death Star. So what it means is that all these services are very highly chatty. They are always like talking to a multitude of other services on the network. There is a lot of touch points for each of the services. And the whole bunch of services make Twitter. Like Twitter is no longer a monolithic application. It used to be a monolithic application back in the day when they were when the company had just bootstrapped and they were basically like a Rails shop. Like I'm not going to get into the details of why monolith, why microservices and monolith versus microservices. But this is how Twitter looks today, and of course Twitter's availability is much higher than what it used to be back in the 2009-2010 era. So what internet scale applications are basically like they're distributed systems, right? And what are distributed systems? Distributed systems are applications like this, which works together, a bunch of services which works together to provide a particular service. That's what distributed systems are at the end of the day. So most internet scale applications are distributed systems, and the principles of distributed systems are pretty much like the six things. Availability. Availability means that the service has to be always available. What it means is, I'll take a real life example, is Netflix. Since I work there, like it's very easy for me to cite. It's okay for us to, it's absolutely necessary for Netflix to be always available. We don't want you to miss Netflix even for a single minute, but it's okay for you to not see the content that you might absolutely like for 5 minutes or 10 minutes. If we provide you some shows that you might like, but not maybe you might want to watch, but you won't be in love with those services for 5 minutes. Like it's fine, but as long as it's available and you are able to access the service, like like you're good for at least for the 5 or 10 or 15 minutes when something bad happens. So that's what availability means. Availability means being up at all times. Availability means being up even when there is some failure in the system. And then performance. We are all used to applications responding really fast, especially front-end services. We are used to front-end services loading really quick on our devices, on our browsers, and things like that. And next comes reliability. Now, people often confuse availability and reliability, and they mix up the two. Reliability has some differences with availability. Reliability means that the data that you have written in your service has to be available at some stage. We should not be losing the data, or we should not be corrupting the data. So if you are using a system like Dropbox, what it would mean that the system has to be highly reliable. That means that the data that you write, at some stage or at some point in time, you need to be able to retrieve it back. Reliability often means that most of the times in distributed systems, making highly reliable service often means that we have to compromise on availability. Because of Eric Brewer's cap theorem, what it means is that systems which are highly consistent cannot be available when there is a network partition and things like that. So in the modern times, there has been a lot of work which has gone into making systems highly reliable, at the same time like keeping them available. One such example of a highly reliable service is Amazon's S3. So what it means is that instead of writing the data and making sure that the data is always available on a single node, the data is written thrice on the network. So if you have 5 servers, like the data would be written on at least 3 servers before the write is acknowledged, so that they can lose one node and they can still recover the data that has been written from the 2 nodes left in the system. So there is like a lot of contemporary research. Peter Baylis has a lot of good papers on how to make reliable systems and with the limitations that the cap theorem enforces, and still have like a highly available system as well. Next comes scalability. So with scalability, what it means pretty much means is that the system has to scale more when we like throw in more machines. This is relevant in the situations when the service has variable traffic patterns or like undeterministic traffic patterns. At certain stage, the system has to grow based on like what users are doing. At that point in time, distributed systems has to be designed in such a way that they can be linearly scaled. One such good example of a system which can be linearly scaled is Cassandra or Riak or anything which was built based on the Dynamo paper, Amazon's Dynamo paper. And then comes manageability. Manageability is really important because if you have run any system in production, you probably know that most of the time spent after a system has been written is like on the operational side. And if you are a team who manages the software along with writing it, you probably understand like the growing pains of running a system which becomes popular over time. What it means is that the system has to, you need to basically have knobs so that like you can turn things on, you can move things around and things like that. When you wake up in the middle of the night, if there is an outage, you need to be able to get information out of the system. So all those things are the manageability aspects of distributed systems. This is a pretty relevant topic and could be a talk in itself. And is very relevant for site operations or site reliability operations when for triaging production issues and things like that. And then comes cost. With all the things that we have already talked about, scalability and performance and availability, what it means is that distributed systems span hundreds or thousands of servers on data centers, and cost becomes like really important. Especially while running on like elastic infrastructure where we are scaling the infrastructure up and down. So these are sort of like the 6 tenets that I think about when I am writing like a distributed system or designing any application which has to be always available and be reliable. This is how I think a modern service tech looks like. And this is based on what I have seen at Netflix and other places that I have worked. At the bottom tier, most bottom tier, you have the cluster manager. A cluster manager could be something like Nomad or Kubernetes or Mesos, which basically powers the whole data center, like where applications are run, how applications are run. In the absence of a distributed cluster managers, you probably have a cluster manager, but those cluster managers are actually like people, like sysadmins. Like in a traditional data center environment, if you're not running Nomad or Mesos or Kubernetes, you probably have like a group of people who are assigning machines to people or teams. So there is some sort of cluster management that is happening everywhere. If you don't have software doing cluster manager, it's like human beings doing cluster management. And then there is like service discovery, and then there is a secret service and things like that. So with service discovery, you get the whole catalog of services that are running in your data center, and you basically...
Sorry, it's me.
So with service discovery, it's all about like getting the catalog of all the services that are there in the system, and then using some kind of RPC or IPC mechanism to reach to them and things like that. On the service discovery front, good examples will be like Consul, Zookeeper, etcd or something like that. And again, if you don't have a service discovery system in your data center, you are probably like hard coding IP addresses. So again, there is some form of service discovery happening in your application or in your environment. You just probably like take it into granted if you're not using a service discovery system. Or like DNS or something. On top of the cluster managers and service discovery lies distributed persistent services like Cassandra, Riak, Voldemort or things like that, or like MySQL, Postgres kind of databases which are ACID, and then object stores which are basically like key value stores like Amazon S3. So the key thing here to know is that in the recent times, there is also this emergence of something called polyglot persistence. So no longer people are designing systems which are running on one databases. People are choosing multiple databases based on the read, write, and availability patterns of the data. So for example, ACID data stores are really necessary if you are, for example, if you need transactions. If you're doing something like payments, or if you're doing something like ticketing systems or something, where there needs to be highly consistent transactions. Whereas with Cassandra or Riak or something, like you'll get eventual consistency, but they will be consistent like at some stage, and you won't lose the data. So if you're designing a system like a tweet service or something like that, like Cassandra is like really useful. Because you want the data to be persistent, you absolutely don't need the data the very next moment the data has been written. And then you have like caches, and then mid-tier services and front-end services, and on top of that you have load balancers. On the right side, it's kind of interesting and been relevant for the last 4 or 5 years is like messaging systems like Kafka. People put Kafka behind their mid-tier services and things like that, which then powered the data or shipped the data that is processed by each of these services to like something like a batch processing system like Hadoop. So what I wanted to portray via this diagram is that any application that is internet scale, any application which is web scale today, are basically like powered by all these different things which are running in your data center. Now, what it means is that your application today is no longer an application. Your application is composed of all this heterogeneous system. And what is common with very heterogeneous systems is complexity and failures. For example, I have been on an outage which happened because our messaging system was writing buffering data on hard disks, right? And what happened was the sync of the messaging system was not working for like 5-10 minutes or something like that. And one of our services, which receives like some 3,000 requests per second or something like that, and we run some 5,000 of those servers, was writing messages to the hard disk for 5 or 10 minutes during which the sync was unavailable, and the hard disk just like filled up, and then the whole service fell down. And because the whole service fell down, services which were in front of it, they fell down as well. So just a failure in one of these systems will bring down the whole user-facing application. So the modern service stack is very efficient. It does a lot of things that we were not able to do maybe 5 or 10 years back. But at the same time, it's also very unreliable. People often claim that microservices are like the silver bullet to everything. But my observation is that microservices are more unreliable than monoliths, frankly speaking. And we have to do a lot of engineering. We have to pull off a lot of engineering muscle to make microservices work really well. If you have been an SRE, if you have been on a pager, like you would probably, you probably see like what I'm saying. Have been on so many outages because of cascading failures. So the data center has changed a lot as well. The data center in mid-80s was pretty much like a single machine, like a mainframe or something like that. I was not there back then, so I don't know how things used to work, but this is pretty much like what history books tell me, that 1980s was all about like a single computer occupying like a whole building. Then came mid-90s, the internet was still quite not there in the part of the world where I grew up. But again, history books say that the data center was like a bunch of racks with like maybe 10s or 20 or 30 servers, very expensive IBM servers. So that's like mid-90s, where we were still running software on very expensive machines and very limited number of machines. Something interesting happened in 2000s, in early 2000, and I think Google was at the forefront of that revolution. Was we started running our applications on commodity hardware, and that changed quite a few things. What it meant by running applications on commodity hardware was that hardware now became cheaper. Corporations were able, or not corporations, like companies, startups in Silicon Valley were now able to buy more servers at the same amount of price they would have paid for a lesser number of machines. And the data center pretty much became virtualized. What it meant was, instead of bare metal, people started running software on virtual machines. And with virtual machines came SAN and SDN and things like that. And the era that we are in today, the modern data center, the data center of circa 2015, is a data center where we no longer only have VMs. We have containers. Containers are pretty much like mainstream now. People are talking about containers. We have virtual machines as well. Some applications run really well in containers, and some applications like applications which need a lot of security and stuff like that, people would still run them in VMs, because VMs still offer a more secure environment than containers. And then we are also talking about unikernels now and RUM kernels now and things like that. For example, a good use case of running unikernel is that recently, like, I was chatting with someone, and I was trying to figure out why they were running unikernels. Someone was saying that with unikernels now, so people love appliances, right? People love appliances because with appliances they can ship like something which does only one thing, like a load balancer appliance, or like a secret service appliance, like an HSM, like a cloud HSM or something. Now these are nice little things which does only one thing, but they are also very expensive. That means that most appliances also come with like a hardware or something like that. But people want like software appliances, and software appliances are also expensive if they are proprietary and things like that. With unikernels, now there is the opportunity of running only one application inside a virtualized environment, and you can ship the whole VM which does only one particular thing. So we are seeing like more of a heterogeneous environment where people are going to be running containers, people are going to be running unikernels, people are also going to be running traditional VMs where they are going to be running traditional applications. And then we also, not only now we have SAN and SDN, we also have like things like cloud storage, for example, right? The data center that we are talking about doesn't need to be on-prem anymore. Like Amazon is data center for many companies now, right? People have data centers on Amazon, people have data centers, they're on-prem data centers, they do direct connect and things like that. So the data center is also hybrid now. So, so what it means is that now we have like so many different things, so the complexity has again increased. For example, if you connect like your on-prem data center with the cloud storage, what happens when the link breaks down? If you are on AWS, you are probably accustomed to direct connect. What happens when direct connect goes down? How does the applications behave? How would your services behave, right? When a developer writes software, like he or she is writing software mostly for the steady state, because that's our nature. We are writing software thinking how things are working when things are perfect. But there is going to be a lot of situation in this data center when the power fails, or the cooling fails, or the network link fails. So there is a lot of, we are already in a complex environment because we are running microservices. On top of that, there is this added complexity of the modern data center, right? So things are quite complex right now. Have you recently seen the job advert for a DevOps engineer? Who has seen, who has gone to careers.stackoverflow.com and seen the job advert for it's for a DevOps engineer? It's like really complex. The DevOps engineer of today needs to know Python, he needs to know Ruby, he needs to know Chef and Puppet, he needs to know distributed systems, he needs to know AWS. I mean, I think like DevOps engineers today are more qualified than, traditional developers like who were doing like stuff in a very traditional sense. So things are becoming really like complex. If you're trying to like hire like a competent DevOps engineer or a platform engineer, like the number of people who would understand so much complexity really well would be like really low. And all this, and why are we introducing so much complexity? We are introducing so much complexity because we want to move faster, right? That has been our mission from the 80s. We want to move faster, we want to deliver software, we want to deliver reliable software, right? So that hasn't changed, but only the complexity has increased. And again, now Moore's law, right? To make matters even worse, like 10 years back, we would know that after 2 years, the software that we are writing today might get faster because processors were getting faster, right? But after the 3 gigahertz mark, like processors haven't like become really fast in the last 3-4 years, right? Because at certain stage, the amount of power consumption needed to increase the clock speed is like so high that it doesn't become economical, or it doesn't become sensible to increase the clock speed. But what is happening instead is the number of CPU cores on a single chip is increasing. So we are used to machines which come with like 8 cores or 16 cores or 32 cores. Like they're mainstream right now, right? But the processing power of each unit might be like some 2.2 or 2.4 gigahertz. So that's pretty much like the norm now. So modern applications must harness the power of multiple cores on a machine, because 2 years from now, the number of cores that they're going to be seeing is probably going to get doubled. And at that time, the application, if it's not using the new cores, it's probably like not making the most out of the hardware. And latencies for accessing data from such processors where you have multiple cores and shared memory varies. So you are no longer guaranteed that the data that you are going to be accessing from the RAM is going to be same same across all the CPU cores. So what it means is that if you're running a database like Postgres on a NUMA server, which has like shared memory and which has got variable latencies, you're going to see variable performance based on which CPU core the process was scheduled by the server. So a modern application should be basically using multiple cores. We should be programming with the assumption that we are running multiple cores, and we should always scale by adding more servers and not by adding more clock speed, because we are going to be seeing more cores anyways, and servers are getting cheaper, so we will have access to more number of servers. And we should scale by running on commodities hardware and not assume that the hardware is going to be reliable. We should tackle the availability concerns at the software level and allow the hardware to fail, allow the network to fail, and things like that. So essentially, the modern application that we are talking about for the last half an hour or something is a data center application, right? It's no longer an application that runs on a single server, it runs across your whole data center. So I like this quote, there is just not getting around it. If you are building a service today, if you are building a service on GCE or on AWS, if you are building using microservices, it's a distributed services. Distributed services are complex, they have very complex failure modes and things like that, but there is no getting around it. And the challenges, the challenges of such systems are manifold, right? The three things that comes to my mind is that faults on a single service can bring down the whole thing, like I said earlier. So it just doesn't, you just cannot trust your own team to do a good job. If your team does a good job in writing the service that you are writing, it's all good and fine, but a service, a downstream service can be responsible for your outage. So what it means is that every network connections you are making, everything that you're talking about the network, like put that under a magnifying lens, see what is happening, see how they can fail, and think about what needs to be done. And debugging faults is harder. When you have a large enough system and the user complains that something is not working, where do you start debugging from? So we had a nice rule at Netflix. It was pretty much like anything that moves on the network has to be measured. Anything that is going out on the network has to be wrapped by a circuit breaker, because we assume that anything that is going out on the network is going to fail. Anything that is doing something has to be exposed via a counter or a gauge or something, so that we can look into it and we can make some reasoning about why it is behaving the way it is behaving at some stage. And then the last thing is unpredictable latencies. If you're running a JVM application, for example, on hundreds of nodes, you will often see that if you're load balancing, sometimes the latency becomes 10 times the latency in a steady state. That can be because of cache, like cold caches. It can happen because of garbage collection, for example, right? So if you have 100 machines, you won't know at what stage each of these servers are doing garbage collection, for example. If you have a service which is, which has a heap of 32 or 36 GB, you should probably see 100 milliseconds or 150 milliseconds of garbage collection time. So that introduces unpredictable latencies. For all these things that I have talked about, there are solutions. We'll see what the solutions are. So the solutions to some of the problems that we discussed can be service discovery. So service discovery systems, there are a bunch of service discovery solutions. There are service discovery solutions like Zookeeper. There is service discovery solutions like Consul. People use DNS as service discovery. So what they do is that they provide the network coordinates of a service. So if you have 100 services in your data center providing a particular, providing the end user application, they need to talk to each other. But how do they discover them over the network? Service discovery is the answer. Zookeeper used to be the granddaddy of service discovery, but it has its own operational challenges. I'm going to talk about Consul here in this talk. What they also do is that they mask the shards of the services in your cluster which has failures. So for example, if you have 100 JVM applications for a service, and if like 2 of them are not doing well because say for example they are using Tomcat and all the threads are exhausted because of like a slow database behind them, the service discovery system like Consul can not expose those 2 services which are doing bad. So for a upstream services which is consuming this particular service, they just won't see the 2 services which are not doing well. And at a later stage when the services are back healthy, the service discovery system can again advertise their network coordinates. So it's very essential that service discovery systems are dynamic, right? So before dynamic service discovery was mainstream, people used to hard code IP addresses in a etc host file or something like that. The reason why they're not good for running microservices on an elastic infrastructure is that at every given point in time, most likely some or a few, like some portion of your cluster is in a bad or degenerate state. At that particular moment in time, it's a dynamic service discovery which will save the day by not exposing the things which are not doing well. And as nodes go up and down, if you're auto-scaling, like your service discovery system needs to handle that and expose the new nodes which comes up and take the nodes which have gone down out of the list of servers for a particular service. So Consul is an open source service discovery tool. It not only like registers and radiates the information of the network coordinates of a service, it also can do monitoring. This is different than the traditional service discovery systems like Zookeeper. Is with traditional service discovery systems, you don't get monitoring. So what it means is that when you add a service to Consul, saying that, hey, I want Consul to radiate this information of where this service is in the network, you can also tell Consul, run this script every 5 seconds or hit this endpoint every 5 seconds, and Consul is going to be hitting this endpoint or run a script every 5 or 10 seconds or whatever period of time you want, and it's going to check whether the service is really healthy or not. And if it's not healthy, it's basically going to deregister that service, and the other services which are consuming this particular shard is not going to see it. So it's pretty dynamic in nature. It uses gossip protocol. That's like another fundamental difference of Consul with traditional service discovery system. What it means is that all the servers in the network are talking to each other and sharing this information of where each of the service lives. What happens as a result is we can do much more interesting things like network tomography. We can use Consul and we can basically say that how much is a service or how far a service is away from another service. So if you have if you have 2 machines of service A and 3 machines of service B, and if A asks for B, A will be given the name of a service which is close to it on the network. So with the traditional service discovery system, they are flat, right? All the IP addresses are like flat, like it's like a single list of IP address for a given service. It's almost like it behaves like DNS at some stage. But with Consul, we can tell you that, you know what, you have 5 IP address for this service, but this IP address is closer than the other IP addresses. So that is only possible because we do gossip. And this really comes into handy if you are running on multiple data centers where the network latencies might be different. So if you have a cluster which is spread across multiple data centers, Consul is like an ideal candidate for doing for service discovery. It also has a consistent key value store, which you can use for storing data which needs to be present across the cluster. Again, going back to the challenges, now we will talk about the challenges at the data center level. The challenges that we talked about so far were challenges at the software level. The challenges at the data center level is that the traffic patterns vary during the day. So at night, you might see lesser traffic than traffic during the day or during the evening. It depends on the service, right? For example, mailing systems will have more traffic during the day or during work hours. or GitHub.com would probably like see so much more traffic during daytime, whereas Netflix sees the peak traffic at 7 p.m. in the evening. So the challenge is that traffic patterns vary during the day, and distributed systems have to scale up and scale down. So that means the resource requirements for your service also varies, and that introduces challenges in data center operations. So when you have more services running, you are probably stressing more. You're stressing the network more during certain part of the day. You're probably using more power at certain time of the day. And if you're running a large enough fleet of servers, you will always see that some portion of your cluster is always in a bad state, right? No matter what, there are going to be hardware failures. There is going to be disk failures. There is going to be like rack failures. There is going to be like PDU failures in switches and things like that. And there is going to be like maintenance. You need to upgrade RAM and things like that on certain machines if you are on an on-prem system. On cloud, you don't get to see those kind of failures, but on the cloud there is no guarantee that machines are going to be up all the time. Amazon might take down a machine whenever it's unhealthy. So those kind of things happen in the cloud as well. So and these are challenges at the hardware level. And traditional data centers are statically partitioned, and it's the system administrator which basically allocate machines to particular teams. And what it means is that during situations like this, where you have API services which are popular during the day and batch processes which are API services which are popular during maybe like early in the day or later in the day, and then you do more batch processing systems in the middle of the day, you will see that the utilization across the data center is very uneven. Right? You'll see machines which are doing batch processing will have higher utilization during the day, and machines which are running APIs will have higher utilization during the time when they are more popular. And what it means is that a company like this is investing in more hardware, because they would need more hardware for doing each of the batch process and API services at different times of the day. But the ideal utilization should be like this. We should be using the same number of machines whenever they are free for doing whatever work we are doing, right? And this is the core crux where cluster schedulers come into the picture. What we are saying is that I want my data center to be like a pool of compute resources. And I want those compute resources, I want to summon those compute resources and run whatever I want. So we were basically, we are saying that we want to decouple compute resources from the work that they are doing. And this is where Nomad comes into the picture. Nomad is a dynamic cluster manager. What it offers, it allows you to achieve higher resource utilization. It allows you to decouple work from resources. It doesn't matter whether you're doing batch processing workload or you're running API services. It doesn't matter whether you're running Kafka or you're running Cassandra. As long as it's a compute resource, as long as it can run an application on it, it will run. And it also ensures quality of service. There are times when an application goes down. What do you do when an application goes down? Do you like wake up in the middle of the night to do it? You will probably wake up in the middle of the night if the failures are infrequent. But on distributed systems, as we have like talked so much, like failures are inevitable. Failures are going to happen. So what it means is that when a service goes down, it needs to be automatically restored. If half of the cluster fails, half of the cluster has to come up, and Nomad helps with that. Nomad will make sure that the cluster is in the state that you want it to be in. So if you want the cluster to have 50 Cassandra nodes, even if 2 of them dies, Nomad will restart them. So that's the idea. So Nomad offers better quality of service. If you have gone to the cluster scheduling talk that Annie did like earlier, so there are different types of schedulers. I'm not going to get into like what are the different type of schedulers. I'm going to focus only on the features of Nomad. And later we will, during the hands-on demo, we will see how all this works. Nomad is multiple data, works across data centers. So what it means is that if you are running 3 different data centers in a given geographical location, you can have a single Nomad cluster which spans multiple data centers. This is different than how Apache Mesos and Kubernetes works, for example. with those systems, you are pretty much like running each of the systems in a single fault domain, whereas in Nomad, you can spread Nomad across multiple fault domains. It doesn't mean that if a single data center goes down, the other data centers are going to be affected. With Nomad, you can evenly distribute the servers, which keeps track of the resources across multiple data centers, so that when one data center goes down, it doesn't affect the other data center. It's multi-region aware. What it means is that if you are on AWS, in AWS terminology, an AWS zone would be a data center, and AWS region would be like a region. So you can say that I want Nomad to be running in every region, but each Nomad region should also know about the other regions. So you can have a control plane, which is maybe scheduling jobs on Nomad, which is asking Nomad to run a particular job. But say so I'll give you an example, right? So at Netflix we do active, right? What it means is we ran our services both on Amazon US East 1 and also US West 2. We were on multiple regions, but if US East 1 failed, we had the luxury of running the whole of Netflix from US West 2. All this stuff is public knowledge. Like if you go and search Netflix active, you'll probably see a talk. In fact, I gave a talk last year about active. But the point is that we want our regions to work as backups. So with Nomad, what happens is if you see that a region is not doing well, you can ask Nomad to query the Nomad API in another region and submit a job or retrieve the state of a job. So you can move containers or workloads that you are running in a given AWS region from one region to another if that AWS region dies. Flexible workloads, Nomad doesn't only run containers, it can run virtual machines, it can run unikernels, it can run containers. Nomad has a concept of drivers. I'll talk about drivers a little bit later. So we have like a Docker driver, we have a Zen driver, we have a KVM driver. So we can do like different types of workload. We don't want you to be in the limitation of having your entire application fleet running on a single type of runtime, because that's not very real. Like we know that people are going to be having different type of runtimes and environments. Nomad has job priorities. What it means is that you can say that the batch workloads are less important than the API services or front-end services. So during the daytime or during the time when API services are popular, even if there is a batch job running, like the batch job would get evicted or it won't get run, and we will run more of your API services because the priority is higher. Nomad does bin packing. It basically tries to make sure that all the CPU or all the memory or all the network in a machine is utilized before it schedules an application on another machine. And we have tested Nomad to run on tens of thousands of machines. Of course, like we didn't do a benchmark yet on tens of thousands of machines, but we have like simulated like how many Nomad clients can our architecture handle, and we have seen we can handle like tens of thousands of Nomad clients. We have done a benchmark on DigitalOcean where we ran a Nomad cluster on 400 VMs on DigitalOcean, and I think we ran like some 8 or 10,000 containers, and we could start the containers in I think less than 8 seconds or something. We are doing like much more real world benchmarking soon, where we will be running like tens of thousands of containers on tens of thousands of machines, and we will report like how long it takes Nomad for Nomad to do that kind of stuff. And we tried the operational experience to keep the operational experience of Nomad simple. We don't want you to be running Zookeeper. We don't want you to be running etcd. We don't want you to be running so many systems just to run Nomad. We understand that Nomad is a foundational system. It's a cluster manager. It lives at the bottom of the stack. We don't want Nomad itself to have a dependency on something else, because if Nomad fails, everything on top of it fails, right? So it's very important that we have a system which doesn't move a lot or doesn't have a lot of moving parts. How many of you have used Apache? Yeah, go ahead.
So like how far is this from being a production system?
It's production right now. Like there are some companies who are using Nomad in production. Yeah. I'm going to talk about the state of Nomad like in a few seconds. And it's a very flexible system. The scheduler is different than the fingerprinters and drivers and job spec and things like that. We have different drivers for doing different workloads. We have different fingerprinters for understanding what type of CPU you have, how many CPU you have. If you have some different types of resources on a machine, you can write a custom fingerprinter to expose that to the scheduler. We have a job specification which is decoupled from everything else. We want sysadmins to be happy. There is, like I said, it's single binary, no dependencies, and it's highly available. We have decided instead of having people run multiple binaries or multiple applications to do different things, we have taken the batteries included approach. What it means is that we have integrated Nomad with Consul. You don't need to run Consul with Nomad, but if you run Consul with Nomad and if you want, we will register a container with the service discovery system. So for example, if you're running Redis, you don't need to do anything else. If you're running Consul, run Redis and we will register Redis with Consul. And you then talk to the service discovery system and then find out on the network what are the IP address of Redis. I'll show an example. And right now we are working on cron jobs. We will also have like a graph-based workflow. So you can run batch processing workload which are invoked periodically or which have dependencies and things like that. Nomad 0.21, which was released like I think 2 days back or something, is really good for services now. So it's doing well for long-running tasks. And with Nomad 0.3, it will be good for things like cron jobs. We have a notion of system jobs which I think is unique, which no one else is doing. What it means is that in a data center or in your environment, you probably run a few things on every machine, like a log shipping agent, like a monitoring system or something like that. With Nomad, you can define them as a system job, and it basically runs, or Nomad, whenever a node comes up or joins the cluster, Nomad will first schedule the system jobs on it. And only when the system jobs are started, Nomad will start scheduling other jobs. So your monitoring system is going to be coming up, and it's like a no-op for you. You no longer need to like provision a system with like a monitoring system and stuff like that. And this is something that is like my favorite feature. I'll tell you a story. The story is from last year when Heartbleed happened. When Heartbleed happened, that OpenSSL vulnerability, like I was literally up for 48 hours. And most of that 48 hours was not because I was manually SSHing into machine and installing OpenSSL 109H, which had the Heartbleed fix. It was pretty much like cat herding, right? It was like calling people and telling that, hey, you know what? Bake all your things. Bake your AMI, bake a new AMI with your application because we patched the monitoring system which used an old version of OpenSSL, right? I don't want that. Now with system jobs, what would happen is, if monitoring systems and logging systems and things like that run as system jobs, I as an operations guy, I can just flip the version of the system job, and Nomad will like change all the applications which I want across the whole fleet. So all the advantage that you have on a cluster scheduler, like rolling update, quality of service, now you can extend them to the core services in an operating system. I think it's really cool. So that's pretty much like what the talk was about. Now I'm going to do a hands-on demo. Do you have any questions till now?